So hello, I'm Jacob Shen from MIT. I actually changed the title of my talk. I was supposed to talk about star formation efficiency and burstiness in the Thiessen Zoom simulation, but I just realized that this might be a better topic to cover in a lightning talk. And I will discuss the connection between early dark energy and early galaxies. So what is early dark energy? It's basically one of the most popular solutions to the Hubble tension. And if you think about how so first of all, the Hubble tension is kind of a 5 sigma difference between the Hubble constant that you measure locally based on the distant ladder versus the one that you can infer from the CMB. And if you think about it, the way that you measure the Hubble constant to the first order is basically using the physical sound horizon at recombination as a ruler, and depends on the angular power spectrum of the CMB, you infer the angular diameter distance to that redshift, and that to first order is proportional to the inverse of the Hubble constant. Well, in this solution, it assumes that there is some hypothetical additional component of the universe that's seeded at very early time, much earlier than the recombination. So that's how the word early comes from. And it has an equation of state that's very similar to the lower redshift dark energy. And what it does is increase the expansion rate of the universe in the early time, and therefore reduce the size of the sound horizon. And then if you use it as a ruler, you would infer a larger value of H0 from the CMB. And that will be fully consistent with what you would derive at lower redshift. And it sounds a little bit contrived, but it's actually described as the least craziest solution to the Hubble tension. And the interesting fact is what it does to the structure formation. At redshift lower than 100, it actually dilutes so fast, much faster than radiation, so that it has no direct contribution to the energy density at late time and no direct impact on structure formation. But it does impose some subtle change to other cosmological parameters. Typically, it involves higher sigma 8 and NS that increase the amplitude of per module fluctuations and nonlinear scales and higher matter density. And the reason is that it will increase the damping of the CMB, and in order to match the same observational measurements, you would need higher per module fluctuations at that scale. And what we find is that if you go through a projector-like theory, this increases the halo abundance at higher redshift, while at lower redshift, it converges back to the lambda CDM prediction. And it's interesting because it kind of goes in the right direction to interpret these early JWST observations. And using a very simple empirical model, we show that for the UV luminosity functions at redshift 12, 14, or even 16, observations can be reconciled with theoretical models with some reasonable value of star formation efficiency or variability or stochasticity of UV luminosity. And in this case, at redshift 14, if you want to match the spectrum or photo D constraints, you will only need a scatter of UV luminosity of roughly 1 magnitude at this characteristic halo mass scale. That's likely the host halo mass of these UV bright galaxies. For the star formation efficiency, that's just roughly 5%, and these are fully within the scatter of simulation predictions. And for the stellar mass density, even if you believe the most extreme observational constraints, there will be no tension with cosmology because this also increases the maximum allowed stellar mass density of the universe in the early dark energy case. And thank you.